Hello, hi everyone, and welcome to the stream. Thanks very much for coming. My name is Robert Palgrave, and welcome to the Journal Club Friday stream. Today, as always, we will be discussing a paper from the scientific literature, but I'll spend a minute or two just introducing the channel, introducing myself, for anyone who hasn't seen the Journal Club before or just wants to know a little bit more about it. So as I said, my name is Robert Palgrave. You can read the name there. So I'm a professor at a university in London called University College London, and I study materials chemistry. I study all kinds of different materials, try to discover new materials to do different things. Maybe I'll talk a little bit about that later on, and teach kind of inorganic chemistry, materials chemistry, things like that. So what this Twitch channel is a place where people can come and discuss journals and discuss scientific articles that appear in the literature. So a journal club is kind of a well-established tradition in a lot of universities and a lot of research groups, in kind of anywhere where people do research, academic research. Often you will find a journal club. So what happens in a journal club is normally there's one or maybe a few, but normally just one or two papers that are up for discussion. So often one person will present the journal article. So they'll kind of outline the main points. They'll go through what they thought was interesting about the paper, what they thought might be the strengths and weaknesses of the paper, any ideas they have because that they might have got from the paper. So they'll present it to the group, and then it's kind of just an open discussion. So anyone can come in and say what they thought of the paper, how it relates to maybe something else they've read, how it relates to their own research, again what they like about the paper, what they don't like about the paper. So it's really just a discussion forum for scientific literature. So the idea of Journal Club Twitch channel is to do that, but on Twitch. So of course Twitch has potentially a much greater reach than the journal clubs that even in the largest research groups, because thousands and thousands of people watch Twitch. So the idea is, let's see how many of those thousands and thousands want to discuss journal articles, discuss some scientific literature. So there's a few streams a week normally. We're just getting the channel started up, so we're very new. Things may change, but there's a few streams a week, and in each stream I will kind of choose a paper, present and present that paper to you guys, and then if anyone is watching in the chat, you can join in the discussion. You can share your own opinions of the paper. So if you're interested in what the paper is, the best way to find out what the paper is, well, you can follow the Journal Club Twitter account, which will tweet out the paper that is going to be discussed, and it did so last night, quite late last night, but it did. But if you've arrived here and you don't want to go to Twitter, and don't go away to Twitter now, what you can do is in the chat you can type !paper, and I'm going to do that for you guys now. So if you type !paper, then the helpful, my camera says a bit weird, I need to sit back. If I go too close I become see-through. If you type !paper, then the bot will reply with a link to the paper that we're going to discuss today. So that's kind of it by way of introduction. I'm debating whether I should try and sort out my my face, if you see what I mean. Let me just try and change some settings and see if that makes anything better. It might make everything a lot worse. There we go. Maybe that's a tiny bit better. Now I kind of have a green halo around my head, but at least I'm not see-through. Okay, great. So what we should do, I guess, is move on to the paper that we are going to discuss. So you can click the link there in the chat. If you come in later and you don't see that link for whatever reason, !paper will always give you the current paper. So I'm going to switch to the pay-per-view. The pay-per-view. This is not a pay-per-view channel. You do not have to pay to watch this channel. But if you do enjoy the channel and you do want to be updated when anything's happened, then there is a follow button at the bottom where you can click. So the paper we're discussing today is this one you can see on the screen. So all the papers that I'm going to choose, I think pretty much, are going to be what's called open access. So open access means that anyone in the world with an internet connection can go and look up this paper for free. So you can just click on the link. You don't need to enter your credit card information. You don't need to supply any kind of bodily organs in order to get access to this paper. Because the kind people at the journal Chemical Science, which is published by the Royal Society of Chemistry, we do not want to restore the pages, thank you. Chrome, not Chrome, what's this? I don't even know what this is called. The Microsoft version of Chrome. The kind people at Chemical Science, published by the Royal Society of Chemistry, make this article open to anyone. So this is open access. It's called Gold Open Access. Just click the link that's in the chat right now and you will be able to access it yourself. So this is a paper we're going to be looking at. It's entitled Synthesis of Double Perovskite and Quadruple Perovskite Nanocrystals Through Post-Synthetic Transformation Reactions. And this is from Hanjun Yang and co-workers. Looks like O-Chen, I may be pronouncing wrong, apologies if I am. O-Chen is the corresponding author, maybe the senior author here. So this is a paper on a really kind of incredibly fashionable area of chemistry right now, and that is these perovskite materials. So perovskite is actually the name of originally it's a name for a mineral. So first of all, perovskite is a name for a mineral, but that's not what this paper is about. This paper isn't about that mineral. The mineral's actually calcium titanate. So CaTiO3 is the perovskite mineral, but this paper isn't about that mineral. So what is this paper about? There's actually, as well as perovskite being a mineral, perovskite is also the name of a structure. So the name of a particular arrangement of atoms is also known as perovskite, kind of confusingly. But these perovskites, compounds with the perovskite structure, have been investigated for a long time. So well over 100 years. And there's been lots of important discoveries made in perovskite materials. So things like magnetic materials. Many magnetic materials have the perovskite structure, used in kind of storage media, data storage media. Certainly in the old days there were. Superconductors, so the high temperature superconductors, which you may be aware of, which become superconductors at liquid nitrogen temperature. These have the perovskite structure as well. There's lots of other things like ferroelectric materials, lots of catalysts, all sorts of things that have the perovskite structure. But that's not what these materials are either. So what are these materials? These materials are a special class of perovskite, which are called the halide perovskites. So what we mean by halide perovskite is that the anion site, the negatively charged ion site, has got a halide ion on it. So halide ions from the halogen group in group 17 of the periodic table or group 7 of the periodic table, depending on your numbering preference. So these form the anions of our perovskite, and these have become very fashionable in the last 10, 15, just over 10 years, maybe 12, 13 years. They've become very fashionable because one particular halide perovskite compound, or a closely related kind of series of halide perovskite materials, turn out to be very effective solar absorbers. So what that means is they can absorb sunlight, and they can convert it very efficiently, almost unbelievably efficiently, into electrical power. So they can be used in a new kind of solar cell called a perovskite solar cell, or PSC. And these kind of materials, as I said, they've been studied for only just over 10 years, so 11 or 12 years. I think 2009 was the initial kind of report on the photovoltaic properties, the solar cell properties of the halide perovskite. And so what's that, 13 years ago now. So 13 years on, we're basically on the brink of commercialization of these materials. So they've gone from kind of completely unknown to almost about to be commercialized in a little around 13 years, which is pretty fast, I think, for a completely new material that's been discovered. And you know, who knows, they may in the end displace the very, very well established solar cell material, which is of course silicon. So if you see solar panels pretty much anywhere, certainly on the roofs of houses, maybe not spaceships. Spaceships can use different kinds of materials, but if you see any on Earth, there's a high likelihood that they're going to be made of silicon at the moment. So silicon is kind of the dominant technology. But who knows? Maybe these new perovskite materials, they may take over. They have a lot of advantages over silicon. There's lots of kind of good points where they beat silicon. So they absorb light much more strongly than silicon does. We say the absorption coefficient is much higher. So that's you know, pretty fundamental property for a solar cell absorber is how much light they can absorb. So perovskites are miles better at absorbing light, and that means you don't need to use very much of them to absorb all of the sunlight that falls on them. Okay, so with silicon you need to use quite a lot of silicon in order to absorb all the light, because it's not actually very good at absorbing light, which is kind of weird for a solar cell absorber, but it's not. But the perovskites are much better at that. Another good thing about the perovskites is that you can make the solar cells with a really kind of simple, low-tech, low-temperature fabrication method. You know, we can make these cells very, very cheaply, compared with silicon, where you need high temperatures, you need very high purity silicon, you need a very energy-intensive process to make silicon solar cells. But with perovskites, much easier to make them, much lower kind of energy intensiveness in producing those solar cells. So there's another kind of big win for them there. Also, some other exciting things, you can change the color of the perovskite. So this kind of sounds like a weird thing. If you want to absorb as much light as possible, why would you not just want to make the solar cell black, because that will absorb all of the light? And indeed silicon is black, so that's kind of a tick the box of silicon there. And you can make the perovskites black. The perovskites can be black, but you can also change their color as well. So we say you can change the absorption edge, or you can change the band gap of these perovskite materials, and that means that you can fine tune their properties. So say that you want a solar cell maybe for a specific application. Maybe you don't want to use it to absorb light from the sun. Maybe you want to use it indoors, or maybe you want to use it in some other scenario where the sunlight isn't the source of energy for whatever reason. Well, with perovskites, you can actually tune the color of the perovskite to make it match the light source as efficiently as possible. So you know, you can in theory, or in some situations, actually produce better efficiencies than silicon and other competing materials. So I've told you a lot of the good points about halide perovskites, and why a huge part of the materials science, materials chemistry, condensed matter physics community has been kind of obsessed with these materials for the last decade. But I'll tell you a little bit about some of the disadvantages of them. So the materials that work the best, and by far the best at the moment, all contain toxic elements. So they all contain, specifically, they contain lead. So lead, as most people know, pretty toxic element. You don't really want lead kind of in the environment very much. It actually builds up in your system if you end up consuming it, which is a very bad idea. It can actually build up in your system and cause kind of long-term damage. So there's lots of regulations about the amount of lead that can be in the environment, especially in things like consumer products. So that's kind of a big problem for the halide perovskites. How do they get around this issue that the elements that they're made of can kill people? You know, how do we get around that problem? Well, that's actually one of I think the most interesting things about the materials and about the research in this area, which I'll talk a little bit about, I'm sure, as we go through this paper in a minute. Another disadvantage of the halide perovskites is that they're not actually very stable. So they're not very kind of tough, robust material. Silicon pretty much is going to stay silicon for forever, you know. So if you have silicon on your roof, the lifetime of those solar cells are going to be 20, 25, 30 years at least. They may well work a lot longer than that. Perovskites at the moment are a lot less stable than that. So that's another one of the big issues that needs to be solved in this field. How do you make them actually more stable? How do you make them so that they can last a year even would be good, or year, 2 years, 3 years, up to 20 years is probably what you need for a commercial product. How do you make the perovskites much more stable? So those two problems, the issue with swapping out lead for something else, so getting rid of the toxic element lead and making the compound more stable, those are both problems that chemists can really get involved in. So those are both chemistry problems, really. So there's a lot of other interesting, you know, fields of research in perovskites. There's a lot of really fascinating physics to do with these materials. There's a lot of engineering in terms of actually making the devices and, you know, making them as efficient as possible. But some of the kind of core problems, I think, are to do with chemistry, and that's what I work in, and that's why I think you know, the perovskites are a really interesting field to work in for a chemist at the moment. There's a lot of potentially a lot of exciting discoveries to be made. Okay, that's kind of a broad intro to halide perovskites. There's so much that I haven't said. There's so much to go into in this topic, but if we do that, then we're never going to actually get onto the paper, and I'm sure some of the issues will kind of come out as we progress through the paper. Okay, so I will read the title again because I went on a little bit of a monologue. So since last time I read it, so synthesis. Oh, let's not highlight everything. Synthesis of double perovskite and quadruple perovskite nanocrystals through post-synthetic transformation reactions. Okay, so let's have a little look at the abstract. I will scroll down a little bit for you guys. So lead-free halide perovskite nanocrystals represent a group of emerging materials which hold promise for various optical and optoelectronic applications. Okay, so the first key thing here is we say lead-free halide perovskite. So that's exactly what I was just talking about before. Getting rid of the lead is a major aim for research in this area. So lead-free perovskites is, you know, that's a big topic. How do we get to lead-free? Well, we'll talk about that in a minute. They actually have some different strategies in this paper to get towards lead-free materials. Freedom from lead, I was going to say. That's a good way to put it. No one ever says that. Freedom from lead is what they're trying to achieve. They have different strategies, but we'll see. The interesting thing, these guys here, they are using, if I can highlight, they are using nanocrystals. Okay, so a lot of not all the work in this area is on nanocrystals. So nanocrystals are a little bit unusual in terms of perovskites. The main kind of the mainstream research in halide perovskites is on polycrystalline thin films. So you deposit a thin film with your material, made up of lots of little crystallites, but they're not nanoscale. Yeah, they're much bigger than nanoscale. In fact, you normally want them to be bigger than nanoscale. But nanocrystals have maybe a whole load of different applications compared to the mainstream materials that I just talked about. So of course what a nanocrystal is a very tiny crystal. So it's a crystal with dimensions, you know, on the order of nanometers. So nanometer is a billionth of a meter, or 10 to the minus 9 meters is a nanometer. So we're going to have particles around that size. So these represent a group of emerging materials which hold promise for various optical and optoelectronic applications. So these could include, of course, photovoltaics, solar cells, but there's actually a whole load of other applications that they may take in as well. So it could be things like LED materials, so light emitting diode materials, for energy efficient lighting. It could be things like X-ray detectors. X-ray detectors are another application of these materials, and there's probably a whole load of other stuff as well. Luminescent materials is another one. If you can dope them with rare earth elements, and you get some really interesting luminescent properties there. So a range of different kind of optical properties, optical applications are possible for perovskites, but also the nanocrystals. Exploring facile synthetic methods for such materials has been of great interest not only to fundamental, I'm doing well with the highlighting today, aren't I? Fundamental research, but also technological implementations. Herein, I might give up on a highlighter. I might just go for it. I might just draw with a pen. Herein we report a fundamentally new method to access lead-free, bismuth-based double perovskites and quadruple perovskites, or layered double perovskites, LDP. Nanocrystals based on a post-synthetic transformation reaction of cesium bismuth halide, cesium-3 bismuth halide 6, where the halide is, so the X represents the halide, so where the halide is chloride or bromide. Zero-dimensional perovskite nanocrystals under mild conditions. Okay, that's quite a long sentence, a few things to unpack. So they're claiming this is a completely new method. I kind of trust them that it probably is. To access lead-free, of course, so everything's going to be lead-free, we take that as given. A bismuth-based double perovskite. So bismuth is one of the main alternatives that people like to use instead of lead. So bismuth is actually the next door neighbor of lead. If you guys want to go and grab your periodic table, if you find lead, go one to the right of lead, you get to bismuth. So bismuth has got a lot of very similar properties to lead. It's got similar arrangement of electrons, say similar electronic structure. It does similar chemistry. It forms all of these kind of compounds with halides. It's a similar size to lead. But the one key difference between bismuth and lead is that bismuth forms a different charged ion. So bismuth forms 3+ ions. Can form 5+, but it's very difficult to form 5+. It basically is not going to do it with halides. You can get it to do it with oxides. It's not going to do it with halides. So bismuth essentially only forms 3+. Lead, on the other hand, forms a 2+ ion. So what that means is you can't just swap out lead and replace it with bismuth, because you're going to have too much positive charge. You can't just replace 2+ with 3+. I mean, you could do it one time, but you can't do it for every single lead in the whole compound, yeah, because they'll have a massive amount of positive charge there, and that's a bad thing. That's going to be very energetically unfavorable. So that's not going to happen. What can happen though is that you can replace some of the lead with a bismuth 3+, and some of the lead with something else, with a different charge, with a lower charge. That's one way to do it. And if you do that, you actually end up with this idea of double perovskites, where does it say double perovskites? Yeah, bismuth-based double perovskites, there we go. So what they mean by double perovskites is a perovskite compound where we have two different cations. So instead of having just lead, we have lead and, we have bismuth and something else. So it could be some, for example, bismuth and silver, which is actually the combination that they use in this paper. So just to summarize, we can't directly replace the lead with bismuth because the bismuth is the wrong charge, but we can replace the lead with a mixture of bismuth and something else. So bismuth being 3+, and there's something else being 1+. And that, for example, could be silver. Silver likes to be 1+. It could be something like sodium. It could be copper. It could be a few other different 1+ ions. But in this case, they're going to be using silver. When we do that, that's called a double perovskite. Now, I was almost finished preparing a few pictures of these structures to kind of get you to have some idea of what the structures are I'm talking about. So this is the structure that I was just talking about, which is called a double perovskite. So as you can see, it's made of lots of atoms, and we're depicting the structure with this what's called a polyhedral depiction. So you can see these kind of these are octahedra. They're kind of these polyhedral shapes. They've got triangular faces. They've got 8 of those triangular faces, so they're called octahedra. The octahedra actually represent the arrangement of atoms around the bismuth or the silver in this material. So the bismuth is actually, I think, this one here. The bismuth is actually the kind of pink ion at the middle of this octahedron. You can kind of see it here. In fact, if I take off the polyhedra, there you go. So the bismuth is here, and around it there are 6 halide ions. These are actually chloride ions. It's kind of hard to see if I don't put the polyhedra on. It's hard to see which halides actually join onto which metal. So this is a bismuth here, this is a silver here. Yeah? It's quite hard to see what joins onto what. So that's why the polyhedral depiction is actually so useful. So you can put the polyhedra, turn the polyhedra on. This is a bit of software called Vesta, by the way, which is actually free software. You guys can download it and have a play with your own chemical structures. But you can see our bismuth ion in here is now, you can see clearly depicted by the polyhedron around it. It's bonded, or it's most closely bonded to these 6 chloride ions around it. And you can see a similar thing happens for the silver ions here. So if we zoom out, we can see the color of the polyhedron in our diagram, of course, represents the color, represents the type of atom at the middle. So the pink ones are bismuth and the gray ones are silver. So we can see we have this very interesting pattern where we have alternating, we have an octahedron of containing bismuth, and then next to it we have an octahedron containing silver. Next to it we have bismuth, and this structure will carry on in all directions forever. So we say that we have ordered or alternating bismuth and silver ions in this structure. So remember, this is called a double perovskite structure. If we had a single perovskite structure or a normal perovskite structure, then all of these octahedra would be the same. They would all be the same color. Yeah, so we could kind of simulate that. It's kind of cheating a bit, but we could do it. Whoops, how do I do it? Let's just make them all the same color. I don't know what color they are. Let's make them all the same color. I think it was this color, wasn't it? There you go. So this is actually what you would have for a normal perovskite. So a normal perovskite would have all of the octahedra the same, but the double perovskite, oh, a bit closer. The double perovskite has this alternating arrangement of bismuth in this case and silver, or two different ions. You can have loads of different double perovskites. So this is one of the interesting structures that people are using to investigate lead-free perovskites. So just to reiterate the point I made before, what they've done is they've replaced the lead, which is a 2+ ion, with a mixture of bismuth, which is 3+, and silver, which is 1+. So the average charge of those metals is still the same as it was before, still the same 2+, the same as it was in the lead, but we managed to get rid of all of the lead. That's excellent. Right, let's go back to the paper where we were before. We're about halfway through the abstract. We're doing well, we're doing well. So what these guys have managed to do, they managed to make nanocrystals of these double perovskites, and actually these other things called quadruple perovskites, or they call them layered double perovskites. They made nanocrystals of them, so they made very, very small particles of these. And they did it not by making those nanocrystals directly, but by making nanocrystals of a different material first, this material, and then transforming that material into the double perovskite. So they kind of did two steps. They first of all made this compound cesium bismuth halide, so CS3BiX6, and then they converted that into the double perovskite in a second step. Okay. So the produced nanocrystals show good particle uniformity, easy for me to say, high crystallinity and comparable optical properties to the directly synthesized nanocrystals. The relatively slow kinetics and stop-on-demand feature of the transformation allow real-time composition, structure, property investigations of the reaction, thus elucidating a cation alloyed intermediate assisted transformation mechanism. So that's a big sentence there, isn't it? That is a mouthful. I think we'll see as we progress through the paper what they're talking about there. What they're basically saying is they made nanocrystals of this first material containing only bismuth. Then they did a reaction to turn it into the double perovskite, but that reaction was pretty slow. So it doesn't happen really quickly. It doesn't happen, as soon as they pour in the mixture or as soon as they press the button. It doesn't happen instantaneously. It happens over a long time. What that means is they can stop the reaction at any point they want. So they could stop the reaction halfway through, where you've half turned it into the double perovskite, but it's kind of half still the starting material, and they can kind of investigate the structure, so that by doing that they can try to work out exactly how this process works. I think that's kind of a summary of what they were saying in this paper, in that sentence. Our study presented here demonstrates the first time that post-synthetic transformation of 0D perovskite nanocrystals can serve as a new route towards the synthesis of high-quality lead-free perovskite nanocrystals, and provides valuable insights into the crystal structure, exotonic properties, and their relationships of perovskite nanocrystals. Okay, so there's kind of not much information, I think, in that last sentence. Is just telling us all how great their paper is, which we are about to find out for ourselves, because we're about to have a read through. So some of the introduction, as normally happens in these streams, I kind of steal away the thunder of the introductions by kind of saying what it's discussing the points before they actually come up. But let's have a little look anyway. Moving away from lead-based perovskite materials driven by environmental and toxicity concerns, lead-free halide perovskites, LFHP, nanocrystals have emerged as a promising family of materials that exhibits great potential in various applications owing to their unique optoelectronic properties and highly adaptable solution processability. Okay, so solution processability, I kind of mentioned, I didn't use those words, but that's basically the easy method of making these materials. Yeah, so it's very easy to make these materials, just in a normal beaker, stirring some different chemicals together in a beaker. You don't need a huge fancy machines. You don't need a huge high-tech factory in order to make these things. You can do it on a bench, in any chemistry laboratory really in the world, which is I think another reason why these materials are so heavily kind of researched, because they're very accessible. Yeah, they're very, very easy to make. Within the family, double perovskites and layered double perovskites, also known as quadruple perovskites, are two widely studied types of lead-free halide perovskites with high structural similarity to the lead-based perovskites in the cubic phase. Okay, scheme 1. So apparently they have a scheme. The scheme is quite small. I'm going to have to zoom in for you guys to see. We can zoom in a little bit here, yeah. And now I'm going to have to look on the other screen to get the scroll bar, otherwise I'm going to miss it. Okay, so here on the left hand side is pretty much what I just showed before. This is the double perovskite. Remember guys, I just sorry, I'm on the wrong screen. This one over here, this is why can I not draw? This is our double perovskite. There we go. So this is our double perovskite, and this is just a different view of the double perovskite, just from a different point of view there. But this is the figure that I showed. Well, I'll show you this figure because it's still on the screen here. So this is what I showed you before. Yeah, so it's the same thing. This is their starting material. So this is the cesium bismuth halide. So they call it A3M. X6. So A is what we call the A site. That's the other metal, which I haven't really mentioned yet. In that case, I think in all of these cases there's cesium. So cesium's a group 1 metal. Kind of boring metal, maybe. I mean, it's not a boring metal. It's a nice metal in that it's very reactive, and it's also almost liquid at room temperature. So mercury is kind of the very famous liquid metal. Actually, cesium's not far off being a liquid metal. You can melt it in your hand. Yeah, so if you have a little pot of cesium and put it on top, it will actually melt. Probably not a good idea because it's incredibly reactive and it's going to react with your hand, but that's fine as long as you take precautions. Hopefully you can't see me. So this is where they start. This is the first compound that they make nanocrystals from, and then they transform it into the double perovskite, and they also transform it the other way into what they call the quadruple perovskite, or the layered double perovskite. So that's a slightly different structure, which I haven't shown you, but you can see the structure here. It's the same idea with the octahedra. You can see the octahedra are less joined together here. So one feature of the double perovskite, which is very attractive and actually very important for applications, all the octahedra join together. In 3 dimensions, in all directions they join together. Whereas here you can see the octahedra are not, some of them are joined together, but like for example there's a big gap here. Yeah, there's some big gaps in this area where there's nothing joined together. So there's some degree of kind of octahedral connectivity, but not as much as in a double perovskite. But in contrast, you can see the starting material, and this is actually pretty interesting. The starting material has completely isolated octahedra. So the starting material, the octahedra aren't joined together at all. They're completely separate. You look at every single one, they're completely separated from their neighbors. They don't join together at all. So we won't go into all of the details, but this is probably a very bad situation, a very bad structure for a solar cell material. Not having the octahedra joined together. You want the octahedra joined together. That allows charge, that allows electrons to move through the structure much more easily. That's what we need to happen if it's going to be an effective solar cell absorber. Anyway, this is the kind of scheme. So they start off, they're just showing different views down here, I think to show some kind of similarity between maybe the structures. But this is the basic idea. They start by making nanocrystals of this, which they, in fact, they showed in a previous paper that they can make, and then they can transform them into either of these two structures. Now, the reason that's interesting, and I probably should have said this earlier, is because neither of these two structures can be made as nanocrystals very easily, or at least we don't know how to do it. We don't know how to do it yet. Okay, so that's the whole point of doing this. They start with a nanocrystal they can make, this one in the middle, and then they do a second reaction afterwards to transform it into one of the other materials. Okay, perfect. So let's zoom out, and we'll go back to the intro. So, let's scroll back up to the intro, which is here. There we go. So we had a look at scheme 1 by replacing every 2 lead cations in A PbX3. So this is the world-beating halide perovskite formulation with lead. So lead is Pb. So replacing every 2 lead cations in lead halide perovskites with a pair of M1 and M3 cations, the double perovskite structure with balanced charge can be formed with a general chemical form of A2M1+, M3+, X6. I quite like to use different letters for M, or at least to have a little dash here to show that M are chemically different. I think here it's kind of implying that M is the same thing, the same element in +1 and +3, which you can have. You can have the same element in +1 and +3. So indium does this, for example. In fact, I think there was a compound with gold does it as well. Gold's another one. I think there was a paper where it had this exact structure with indium, and it's definitely one with gold in it as well. But it doesn't have to be the same. Yeah, so M can be M1+, or what they call it, MI, and MIII can be different things. That's pretty important to realise, and they do state that underneath. But you know, you could use different letters, or put a little prime to show that they're different. Anyway, the resulting double perovskite lattice is composed of alternating octahedra, which construct a cubic framework through corner-shared halide X- anions. Scheme 1 on the left. Yeah, this is what we saw before. This is the structure we went through before. So corner sharing is just the way the octahedra join together. That's all it means. Where are we? Up here. Blah 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 blah. One step further, when replacing every 2 M1+ cations in a double perovskite with 1 M2+ cation and 1 vacancy, so vacancy is a missing ion, the layered double perovskite structure with a chemical stoichiometry of A4, M2+, M3+, 2 times, X12 can be attained with an ordered sandwich structure. We're back on sandwiches. Anyone who watched the first stream, there was a lot of discussion of sandwiches in that stream. I don't know. Would you call this a sandwich? I guess here's a sandwich. I think a sandwich has to have a different filling to what's on the outside. It has to. Surely, that's literally the point of a sandwich. So if you were making a sandwich, you wouldn't get 2 slices of bread and put another slice of bread in the middle and call that a sandwich. That's just a small loaf of bread. So I wouldn't call this a sandwich, to be honest with you, because this and this and this are all the same. The layers, I get what they mean. Here's some layers, here's another layer, here's a third layer, but all of the layers are the same. It's not a sandwich. Sandwich has to have something different in the middle. So I think maybe, maybe I need to write a paper about this to get sandwich terminology. It's not. I disagree with their characterization of sandwich. Layered, yes, definitely layered structure. Not a sandwich, surely. Between two adjacent vacancy layers along the direction of the original DP lattice. Intriguing optical and optoelectronic properties have been reported for double perovskite and layered double perovskite nanocrystals. So as I said before, most of the work on this is not on nanocrystals. Most of the work is on just polycrystalline thin film materials or powders even. Nanocrystals are very much smaller than that, and so just by virtue of them being so small, they can have a lot of different properties. And just by being so tiny, that can actually induce a whole lot of different properties, and there's loads of examples of nanoparticles having different properties, in a massive range of materials. Gold nanoparticles being completely different to, a lump of gold, silver, noble metal nanoparticles, loads of stuff really. Anyway, For example, okay, they're going to give some examples with some things like self-trap excitons and external phonon coupling and vacancy. Okay, we're not going to go into that stuff. Making things in nano can sometimes change their properties. That's I think what we want to. That's what we want to take away. Vacancy order double perovskites, including cesium tin halide, cesium zirconium halide nanocrystals, exhibit unique thermally activated delayed fluorescence with tunable photoluminescent profile. PL is photoluminescence. I don't know if they've actually defined that. Maybe they did. Photoluminescence profile and high photoluminescence quantum yields. So luminescence is when you shine light on something and it gives off light. Yeah, so shine light on, it gives off light. The quantum yield is when you shine 100 bits of light on, how much light comes off. That's the quantum yield. So in this case, you shine 100 bits of light on to your material and 60 bits of light comes off. That means you have a quantum yield of 60. What happens to the rest of the light? Well, it just gets transformed into different kinds of energy. So normally just be used to heat the material, end up getting hot, basically. But so yeah, photoluminescence, shine light on something, it gives off its own light. You'll be familiar with that. So you've seen it if you shine UV light onto stuff, especially kind of white, like paper or stuff that's clothes that have been in had detergents on. When you shine ultraviolet light on something, it gives off its own light. That's luminescence or fluorescence, same thing. The cesium, copper, antimony chloride. So they're just giving a lot of examples of different materials which kind of do different things. So we're probably not worth going through all of those examples. Let's look to, okay, this may be interesting here. Yet, unlike lead halide perovskite nanocrystals, injection-based synthesis of double perovskite and layered double perovskite nanocrystals encounter more problems due to involvement of increased types of components as well as other possible reaction side products, oftentimes leading to poor purities. Oftentimes is a great word. Oftentimes is fantastic. Oftentimes leading to poor purities in the product composition and or crystal phase. To alleviate this problem, indirect synthesis strategies for halide perovskite nanocrystals involving converting pre-existing nanocrystals to targeted materials with desired compositions and crystal phases have been proposed and demonstrated. In this regard, zero-dimensional perovskite nanocrystals with isolated metal halide MX63- octahedra have been prototyped as an ideal starting material for transformation reaction scheme 1. This is what we just looked at. The metal deficient stoichiometry of 0D perovskites offers a strong tendency of transforming to other perovskite type phases upon external stimulation such as varying solvent polarity or introducing additional metal halide precursors. For example, the transformation reaction of cesium lead halide, cesium 4 lead halide, 0D perovskite nanocrystals to obtain uniform cesium lead halide 3D perovskite nanocrystals has been successfully demonstrated. Okay, so what they're kind of saying, let's zoom in on here. Let's zoom in on here. So they're saying that, do I have a hand? No, I have to use the scroll bar. Sorry, I have to look away from you guys to use the scroll bar. What they're saying is this structure, because this structure's got so many gaps in it. So you can see what they talk about gaps here. Sorry. So for example, let's change. It's too much blue. Let's go for green. So for example, there's a big kind of gaps all through the structure. Yeah, there's lots of areas where you could, in theory, place another metal ion. There's lots of gaps in here. Yeah. So they're saying that gives you a lot of flexibility, and it kind of opens up the possibilities of inserting extra ions into this structure to fundamentally change the structure into something else. In contrast, this structure doesn't really have any of these gaps in. You see, everything's pretty tightly packed together. In some ways, this is a close packed structure. So there isn't really any space to put new ions in here. You might be able to swap ions out from this structure on the left hand side, this double perovskite structure. You might be able to swap ions out, and in fact, you definitely can do that. But it's typically a lot slower to do that than just to kind of insert ions into a space. So this is their strategy. They can make nanocrystals of this, and this is easy to make nanocrystals of because it only has one, or let's say it has fewer components. It has fewer elements involved. So it doesn't have, if you compare to this structure here, this has got 1, 2, 3, 4 elements involved, whereas this one has only got 3 elements involved. Yeah, an A element, so it's going to be cesium, an M element, that's going to be bismuth, and an X element, that's going to be chloride or bromide. Yeah, so it's only got 3 elements involved. This one's got 4 elements involved. The one on over here, which I have to find a scroll bar, has also got 4 elements involved. 1, 2, 3, 4. Yeah. So their point was making nanocrystals of this something with more elements is harder, because you might accidentally make a whole lot of different other compounds that you didn't mean to make. Maybe you might just end up with a compound with only 3 of these elements in, and the other one just like hanging out and not doing anything. You might accidentally make the wrong compound. Whereas if you have fewer elements in there, there's not that many different possibilities of things you could end up making. So it's easier to make with nanocrystal synthesis, easier to make these ternary compounds, with ternary means containing 3 elements, than it is to make a quaternary compound that means containing 4 elements. Yeah. So their strategy is make this as a nanocrystal, then exploit the idea that there's lots of holes, lots of spaces in this material that you could fit extra ions in, and just fill them up with, in a second step, with the other metal that you kind of want to use. Okay, let's zoom all the way out. So where were we? We were somewhere along here. Yeah. So they're telling us this is a better way of doing the nanocrystal synthesis compared with trying to make it all in one go. Okay. Herein we present a fundamentally new approach to access 2 important classes of lead-free halide perovskite nanocrystals, and we already know what they are because we already read the abstract and discussed it at length. So we can probably skip through most of this. Thus the reaction, okay, so this was an important point. Importantly, unlike the fast reactions during direct synthesis, that's making the whole thing in one go, as opposed to in 2 steps, which is what they're doing here, more controllable and slow reaction nature of the post-synthetic transformation process allows us to closely monitor the reaction evolution and capture intermediate products. Thus the reaction mechanism can be studied, delineated as an alloy, okay, what they're telling us, as an alloy intermediate assisted intraparticle transformation process for both DP and LDP cases, that's double perovskite, layered double perovskite cases. Wowzers, okay, we'll look at what that means in a minute. In all, our study provides not only a new route towards fabrication of high quality lead-free halide perovskite nanocrystals, but also provides a powerful platform which enables deeper understanding of composition, structure, property relationships of such fascinating materials. Okay, I think they've done a really good job of selling their work there. So they're really trying to put this in context of it's not only about these specific materials that they've made. It's not just the 2 or 3, I think maybe they made 4 different compounds in this paper. It's actually about a new methodology. I've tried to I think talk a little bit about that. It's this indirect synthesis, making a simpler nanocrystal first, then transforming it in a second step. And that also, as well as being a good route to make the desired compound, it also allows you to, because that second step, that transformation step is very slow, it actually also allows you to study that process. So how does that transformation happen? You can actually watch it happening kind of in slow motion, So it's like if you want to watch, I don't know, if you want to watch a magician, let's go with that analogy. You want to watch a magician, this used to be my hobby on YouTube. YouTube basically kind of, I think has kind of killed, I'm not going to say killed magic, but it makes it way easier to find out what the hell is going on when magicians do their tricks. Because on YouTube, and you may be watching me on YouTube right now, you can set the playback speed, and you can set the playback speed to 0.25, as in like a quarter speed, or maybe you can even go lower than that. So basically any magic trick that you want to find out how they do, find someone doing it on YouTube and then just watch it in kind of super slow motion. So you find out how the magic trick works, but also I think you gain a bit of appreciation for how skilled many of these magicians are. But the analogy here, which I think there was one at some point, maybe at the beginning, was that by slowing everything down, by doing that second step in kind of ultra slow motion, you can actually see what is going on. You can see how we go from here. How do we go from here to here? How does it actually happen? That's I think what they're kind of they're trying to show us here. So it's not just a paper about synthesis of 1 or 2 or 3 or 4 materials. It's actually kind of a new methodology for studying these kinds of reactions. Yeah, so I think they did a really good job in the intro, in the abstract as well, of selling their paper. of really kind of emphasizing the merits of what they've done, and how, you know, that could be used by lots of other people as well. All right, as you may know, if you've ever watched this stream before, I still do not understand why we go straight from introduction to results, and they don't tell us how they make it, because that's kind of, especially what I've just said, because it's a methodological paper. You know, I want to know how they do this stuff. We go straight to discussion, and then we might think, oh well, you know, if you just look in the rest of the paper, then you'll find the experimental. No experimental here. So in fact, you have to go to the supporting information, electronic supporting information. So I'm going to leave this here. I'm going to flick over to the supporting information, and we can see how the hell they did it. So this is the supporting information, not gone through the journal formatting process. So this is just as written in possibly Microsoft Word. Looks kind of wordy, and this kind of contains all of the maybe less interesting details. But if you actually wanted to do the work yourself, you know, this becomes really important. Okay, here's a whole list of chemicals that they use. I'm not going to read that out. What I'm interested in is the synthesis. So the synthesis procedure of, so these are the ternary perovskite, if you want to call them perovskites. This is a ternary compound. So this is the first compound they make, and then after they make it, they're going to turn it into the other compound later on. So, but first of all, we need to make this thing. So the synthesis procedure of these nanocrystals is based on a previous report mentioned method by our group with minor modification. Okay, so we can go and look up their article if we want. Bismuth acetate, cesium carbonate was mixed in ODE. ODE is 1-octadecene. So that's I'm guessing that's a liquid. It's going to be pretty, I guess it's going to be pretty high boiling point. Don't really know much else about it. So OA is olalamine, I'm pretty sure. Sorry, oleic acid. Olalamine is OAM. Oleic acid and olalamine, and degas at 90 degrees under vacuum. Okay, so probably you can hold this stuff under vacuum because it's not really going to boil. I think ODE is probably going to be 10 chain, 18 chain carbon. That's going to be difficult to vaporize. Afterwards, the mixture was heated to 160 degrees, when a mixture of 0.8 mils of benzyl halide and 0.8 milliliters of ODE, I guess mixed together, was rapidly injected. The solution was immediately submerged under ice water bath and cooled down to room temperature. The resulting nanocrystals were separated from the solution by centrifuge for 5 minutes and purified twice by toluene and ethyl acetate. The resulting nanocrystals were dispersed in toluene or hexane for further use. Okay, so this is what's called a hot injection method. So you dissolve one of your starting materials in this high boiling point solvent. You add in the olalamine, so the oleic acid and the olalamine, and what they do, these are surfactants. So these will bind onto the surface of the nanocrystal. The difficult thing about nanocrystals, so the reason why making nanocrystals is hard, is because nanocrystals don't really want to be nanocrystals. Okay, nanocrystals would like nothing more than to stick together to form something that's not nano anymore. They're going to keep sticking together until they just form big clumps of stuff which is not nano. The reason they want to do that is because the surface of a nanocrystal is a region of high energy. Yeah, the surface of a nanocrystal is a region of high energy, and it can the system can lower its energy by destroying two surfaces. It can destroy two surfaces by just sticking two particles together. Yeah, sticking two particles together, you destroy two surfaces, and so you lower the energy of the system. So if you want to make nanocrystals, you have to stop that from happening, and the way you do that is with surfactants. So you need something which is going to bind onto the surface of the nanocrystals as they're growing. Yeah, if you don't have that surfactant right there as you grow the nanocrystals, it's gonna happen too fast. The nanocrystals are going to stick together. By the time you put in your surfactant, it's kind of too late, guys. So hot injection, you have one of your precursors, one of your starting materials. You have the surfactant already there, which is these guys, and then you inject in at high temperature with a lot of stirring. You inject in the second reactant, which will react with the first one to make the nanocrystals, and that will then happen very rapidly but because you have such a high concentration of the surfactants there, they will quickly bind onto the nanocrystals as they form, join onto the surfaces, lowering the surface energy that way instead of by the nanocrystals themselves fusing together, and you have your nanocrystals formed. So that works as it seems very well for the cesium bismuth halide, but as we said before, you can't access directly the double perovskites that way. So let's see how they then did they centrifuged it to separate it. They purified it twice with some methods. That's not so interesting for us. Okay, let's see how they do the next step. So in a typical reaction, 5 mils of the nanocrystal hexane dispersion, which they just made before, with 5 mils of oleic acid and 5 mils of oleamine was heated to 50 degrees under constant stirring. Certain amounts of 10 milligrams per milliliter silver nitrate solution in acetonitrile were added slowly to the cesium bismuth halide dispersions until a ratio of silver to bismuth reached 1:1. Okay, so they're slowly adding in the silver. It's basically a similar method to what they did before, except instead of doing everything very fast, they're now doing everything very slow. So they're very slowly adding in the silver. They're a much lower temperature than they were before. They were 160 Celsius before, now they're at 50 Celsius. Okay. Until the ratio of silver to bismuth reached 1:1. Okay, so they work out how much silver they have to put in and they slowly add it in. After each addition, the solution was allowed to react for at least 30 minutes until no further change in the absorption profile was observed. So I don't know if I wonder if they measured the absorption profile or if they're just looking at it. After the reaction was completed, the reaction solution was centrifuged again. Okay, so that's kind of basically it. You add in your silver nitrate. You do the hot injection to start with, and then you kind of do a cold, slow injection as the second step with silver nitrate in order to make that compound. Okay, so let's have a look at their discussion. So the first part says what we already know because we took the time to go and read the supporting information. Zero-dimensional cesium bismuth halides were first synthesized using our previously reported method, which we just read about. The crystal structure is composed of isolated BiX6 3- octahedra, which you know, leading to a 0D electronic structure with molecule-like optical properties. Okay, fine enough. So 0D electronic structure means that the electrons can't move. They're kind of trapped on each bismuth octahedron. Yeah, they can't move around so easily. The resulting 0D nanocrystals show characteristic sharp absorption peaks at these wavelengths for the chloride and the bromide nanocrystals respectively, and we can go look at those if we want to, but probably not that interesting. Neither cesium bismuth chloride or cesium bismuth bromide 0D perovskite nanocrystals exhibited any. Let's have some. We forgot about the music. Let's have a bit of music. Let's go with this. The resulting 0D nanocrystals show characteristics. Sure, I read that already. Neither of them exhibited any detectable photoluminescent signal at room temperature. Okay. The X-ray diffraction patterns of both samples confirm that the monoclinic crystal structure of the 0D perovskite. I'll go and have a look at the XID. I'm always up for looking at a bit of XID. Figure S1. Figure S1. I haven't looked at this already. Here we go. S1B. All right. So you can see. So the XID here, if you guys are familiar with looking at XID, I guess this isn't too untypical for a kind of XID of a nanocrystalline material. Very, very broad peaks. Yeah, very, very broad peaks here. That's because the size of the diffracting region, the coherent diffracting region, is very small because it's a nanoparticle. So that means that certain assumptions in Bragg's law are no longer relevant. So Bragg's law assumes you have an infinite crystal, for example, and so that you tend to get a broadening of the XID peaks, which is maybe kind of typical here. This is the absorption spectrum, I think. Let's have a look. What's A? A is the absorption spectrum, yeah. So absorption spectrum, okay, you get these peaks which they mentioned before. Also, they've got some nice pictures. So yeah, pictures are always nice, especially when you're doing nano stuff. It's always nice to actually see them. And you can see these nanocrystals really nicely here. Let me just get the slider at the bottom. And there we have the two different flavors. We have the chloride flavor here, and we have the bromide flavor here, and you can see, yeah, these are indeed nanoparticles, well under 50 nanometers, probably around 10 nanometers. I'm sure they tell me. They also did some selected area diffraction here, which is a nice way to understand the actual atomic structure of the crystals, but we of course have the powder XID, which kind of also helps as well. Great. Okay, let's scoot back to here. So neither I'm showing you photoluminescence, the XID. So the nanocrystals exhibited a cubic shape with an average edge length of 7.7. I said about 10, didn't I? I said under 10. Not bad estimate. Respectively, the obtained high quality cesium bismuth halide nanocrystals were used as starting material for the post-synthetic treatment reactions described below. Okay, so let's have a look at this. Post-synthetic transformation reactions from cesium bismuth halide 0D perovskite nanocrystals to the double perovskite was carried out by adding acetonitrile solution of silver nitrate to the cesium bismuth halide hexane dispersion. And we already read the details. The reaction conducted at 50 degrees for 24 hours and monitored by UV absorption and photoluminescence spectroscopy. The low miscibility between hexane and acetonitrile facilitates the separation of nanocrystals from the silver nitrate precursor, and the reaction temperature was chosen to avoid solvent evaporation. It makes a lot of sense. The occurrence of cesium bismuth halide nanocrystal transformation reaction was proved by the emergence of a new absorption peak at 362 nanometers and gradual disappearance of the 323 nanometer absorption peak for chlorine and bromine based samples. In addition, a broad photoluminescence peak centered at 672 with a forward half maximum of 0.69 electrovolts was detected. Okay, so they're saying that they can tell that their structure is changing because the optical properties become completely different. You get an absorption peak at a different wavelength compared to the initial material, and you now start seeing photoluminescence, which is a characteristic of the perovskite, of the double perovskite, but not of the initial starting material, not the initial nanocrystal. You start seeing this photoluminescence peak coming in at this particular wavelength, and this is the evidence that they're providing, which seems pretty reasonable, that this transformation is actually occurring. Double perovskite nanocrystal samples which unambiguously confirmed, the photoluminescence excitation spectra overlap with the absorption profiles of the final nanocrystal sample, which unambiguously confirms that the photoluminescence originates from the band gap absorption of cesium, silver, bismuth halide. Okay, so that's a nice way that you can do to find out when you have photoluminescence. You want to know where does the photoluminescence come from. So photoluminescence comes from absorbing light and then giving out light again. But what light are you absorbing to give out that causes the light to be given out? So that's what photoluminescence excitation measurement does. So they were able to match up the photoluminescence peak coming out with the light going in, which matched the absorption spectrum of the double perovskite, the cesium bismuth halide. And that showed that's another bit of evidence, I think, which shows that the PL is coming from this new phase that they are making. Okay. They had a figure. That's scheme 1. That's scheme 1. Figure 1A is here. Okay, here we go. So figure 1A shows the emergence now of the photoluminescence peak. It is very broad photoluminescence peak here. The absorption peak is here, and the PLE. The PLE is measured. So you measure the intensity of light which comes out here as you change the excitation wavelength, as you change the wavelength going in. Yeah, so that's what this little dotted line is, and you can see the little dotted line matches up very well with the absorption spectrum of the cesium, silver, bismuth, bromide, and indeed with the bromide as well. Kind of shows that that's where the photoluminescence is coming from. Great. XRD, the final samples confirm the structural transformation from the 0D to the 3D cubic double perovskite phase, figure 1B. Here we go. So this is actually we saw this before. This is the nanocrystallite XRD that we saw before, and we can see after reaction. So here we are starting with cesium bismuth chloride, the original nanocrystals. After reaction, you get actually it looks like much sharper peaks, doesn't it? Possibly it's just because the cesium silver bismuth chloride is higher symmetry, so it's got fewer Bragg peaks, fewer diffraction peaks. So it might be just you have lots of peaks kind of overlapping here. It's hard to tell. But here the peaks maybe look a bit narrower. Maybe that's just the higher symmetry that I'm being swayed by, as I said. But so these peaks, definitely different diffraction pattern. Some similarities, but definitely if it looks a bit different. This peak especially, I think, is kind of indicative. And you have a similar thing going on up here as well. So yeah, looks good. You have a transformation of the optical properties, transformation of the diffraction. Let's see what else they got for us. Let's see what else they got. The disappearance of characteristic 0D perovskite diffraction features, for example, the absence of signals in the 2 theta range from 30 to 32.8 degrees, correspond to those peaks. Okay, they're convincing us. It's all right. We're convinced. We're convinced that it's a different material. Crystallite sizes of the produced double perovskite nanocrystals were estimated by Scherer analysis to be 7.9 and 7.8 nanometers for cesium bismuth, cesium silver bismuth chloride, cesium silver bismuth chloride nanocrystals respectively. Okay, Scherer analysis is a kind of analysis you can do on the width of the peak, and the broader the peak, the bigger the broader the peak, the smaller the crystals are. Again, for the same kind of reasons I mentioned before, the assumptions in Bragg's law, the fact that you have a much smaller coherent diffracting volume means that your peaks get wider if you have very small crystallites. So you can measure it. Most people, would definitely prefer TEM measurements, which they have done. Scherer analysis can be a little bit dubious. I think many people think that, but the fact it matches up with the TEM in Figure 1C. Let's have a look at Figure 1C. Looks good. Yeah, Figure 1C there. I don't know why C is here and F is here. That's very confusing. But anyway, Figure 1C is down here. So these are the transformed nanoparticles, and I think these are probably the starting materials in F. They're the starting materials. No, these are the bromide, I think, and these are the chloride, maybe. I have to read in detail. Anyway, nearly unchanged particle size and morphology between the starting and final nanocrystal suggested the preservation of individual nanocrystal integrity during the transformation reaction. Yeah, absolutely. I mean, you could think what might happen, maybe what would have happened, is that these particles just kind of stick together during this process. It looks like that's not what's happening. So they're not doing that. They are actually, each individual particle kind of maintains its integrity, but you're just kind of very gradually adding in the chloride, adding in the silver into the structure, the original structure, to form your double perovskite. The drastic structural leap from 0D to 3D perovskite motivated us to investigate the structural evolution mechanism. Too right. Makes a lot of sense. How does this happen? The relatively slow reaction kinetics and stop-on-demand feature of the transformation allows us to fine-tune the silver concentration as well as closely monitor the transformation process of this model system. In contrast to the injection-based synthesis routes, which exhibit rapid reaction kinetics that hinder real-time monitoring of the reaction process. Yeah, that's kind of what I said before. So because this is much slower, this is like the slow motion magician on YouTube, compared to watching it in real life. You get one chance to see it. You're never going to see what happens. You're never going to see him switch the card to the back, or put the rabbit under the table, whatever. But with YouTube, with slow motion, you can do it, and that's kind of the analogy here. We're looking at the reaction in super slow motion, and by doing that, you can understand a lot better what's going on. Okay, let's have a look. XRD measurements show. So XRD is the first tool they're using. Remember, XRD tells us about the crystal structure. We already know that there's a big crystal structure change between the starting material and the ending material. So a really good question: how does that process happen? What happens kind of in between these two? What happens between the starting material and the ending material? What happens in between? Hopefully, we're about to find out. I think we are. I think we are from this figure down here. Let's read a bit anyway. XRD measurements show that with increasing the feeding amount of silver, so the more silver they put in, the crystal structure gradually changed from initial 0D monoclinic phase to the 3D cubic phase structure. The cubic double perovskite structure started to emerge when the stoichiometry ratio between silver and bismuth reached 15%. Given the low concentration of silver ions, the silver doped 0D cesium-3 bismuth chlorine 6 nanocrystals coexisted with the alloyed double perovskite nanocrystals, with the M1 sites occupied by either cesium or silver cations. Upon further, let's maybe look at the XRD in a second, and we'll try and unpack that. Upon further increasing the silver precursor amount, the double perovskite diffraction features become prominent, revealing an increased contribution from double perovskite crystal phase. Besides, all of the double perovskite crystal peaks shifted to larger 2 theta angles, indicating continuous lattice contraction during the reaction. In line with the insertion of small silver cations, ionic radius 1.15 angstroms into the metal 1 plus site, and replacing the larger cesium cations with a larger ionic radius 1.67 angstroms. Okay, interesting. Let's maybe do they have some? Let's look at the pictures. That's, I think, with a lot of these structural things, looking at the pictures is maybe a good way to understand better. We can go back to the text. All right. So what they're saying is, right. Okay. So they're saying the first step is that the silver comes in and replaces some of the cesium, yeah, to make this kind of alloy. So cesium 3 minus X, silver X. So some of the cesium here is being first replaced by silver. So you can see these little dots here. These are the these ones here are some of the cesiums replaced by silver. Okay, I think this is a cesium as well. It looks like it's kind of part of the octahedron, but it's not. I think it's in front. So then what happens after a little bit more is added? You start to get what they call a double perovskite motif. So you'll notice that the silver, when it replaces the cesium, it's actually in a very different coordination environment, a very different kind of, has very different surroundings compared to where it's going to end up. So it's going to end up octahedrally coordinated, the same as the bismuth, yeah? So all the way, remember back to our original idea here. Here's the silver, it's in the middle of an octahedron, yeah? It's octahedrally coordinated. So the silver is eventually going to end up like that, but what they're saying is that it doesn't start like that. It doesn't start by going in as just replacing some of these octahedra. You might think, oh, it's going to swap out the bismuth. It doesn't swap out the bismuth. It actually swaps out the cesium, and the cesium is on a completely different site. The cesium is probably, I don't know about that structure. I'm not smart enough to do it in my head, but it's probably 12 coordinate. So it's probably got 12 things around it, some kind of distorted way. Whereas the silver is going to end up, so it starts off being 12 coordinate, it ends up being 6 coordinate. So that they're saying that process happens in this next step. So after you get a certain amount of silver in here, you start to form what they call a double perovskite motif. So that's where you start to fill in these gaps here. Remember we talked about the gaps earlier on in this original 316 structure, cesium bismuth chloride structure. You start to fill in the gaps with the silver octahedron. So now we start to see the silver octahedron, but we still have some of the silver on the cesium sites as well. So now we have kind of a mixture of the silver on the cesium and the silver in this octahedral formation. And then eventually, as we go over here, it says we then have, later on we have a phase transition where we have now, oh, okay, interesting. I'm going to have to go and read the text. It looks like from this they're saying that you actually have cesium on an octahedral site. I think that is what they're saying. That is what they're saying from the formula. So they're saying you have cesium on the A site, then you have a phase transition where the cesium is on some of the octahedral sites. That's very interesting. I'm not sure I've seen that suggestion before, but I may just be out of touch. So that these light blue ones, the cesium now becoming octahedral, pretty unusual, I think. Silver is on the octahedral site here, and bismuth is kind of the dark blue. So silver is the red, and bismuth is the dark blue here. Then eventually we get to the complete transformation where the silver finishes substituting out the octahedral cesium to form our double perovskite. Okay, let's go and read the text on that because I'm quite interested about the whole. Whoops, that's the wrong screen. I'm quite interested about the concept of the cesium being octahedral. Let's see what they say about that. With increasing silver concentration, okay, now they're talking about they talk about the Raman down there. Let's see what they were saying here. The insertion of silver plus cations and a corresponding local structural change were further supported by X-ray photoelectron spectroscopy, where the silver 3D peaks of the sample showed enhanced intensity with increasing silver to bismuth ratio. Okay, so they did some XPS. We'll go look at that in a minute. That just measures the amount of silver in there. So they're just saying, yeah, we really put silver in. That's kind of fine. At 0 point, okay, they talk about the binding energy. I normally like to talk about XPS, but I'm more interested in this idea of the cesium on an octahedral environment. I want to see what they say about that. Such gradual insertion of silver plus cations was also confirmed by the energy dispersive X-ray spectroscopy measurement This structural change during the transformation can also be reflected by the Raman spectra evolution in 2D. Okay, before we go into Raman, we never actually looked at the XID. Let's zoom in on the XID here. Whoa. Too much? Maybe too much. Okay, so maybe still too much. Okay, maybe one less than this. Perfect. Okay, so at the bottom we have our original nanocrystal, the cesium bismuth chloride. At the top we have our finished product, our cesium silver bismuth chloride. And then in the middle we have this kind of gradual change. And you do kind of see a gradual change as these go, as you introduce more and more silver. I'm not entirely sure where they're saying the phase transition is. Are they saying it's here? Are they saying it's at 40%? It doesn't look like there's one point where it suddenly shifts. It's kind of, everything seems a bit incremental, but maybe I'm reading that wrong. What do they say about phase? Yeah, so the cubic double perovskite crystal, let's see about that more. The cubic double perovskite crystal started to emerge when the stoichiometry ratio between silver and bismuth was 15%. Okay, so 15% is here. Okay, so they're saying this is the start of the emergence. The emergence is happening here apparently. Okay. But upon further increase in the silver precursor amount, the double perovskite crystal feature become more prominent, revealing an increased contribution from DP crystal lattice, from the DP crystal phase, sorry. Besides, all the double perovskite diffraction peaks shifted to larger 2 theta angles, indicating continuous lattice contraction in line with insertion of small silver ions onto the M1 side, replacing larger cesium. Okay, so we talked about replacing the cesium. What I'm most interested in is where they get the idea that the cesium is on the octahedral side, whether they have actual evidence for that. Doesn't seem like they're mentioning it here. Doesn't seem like they're mentioning it here. I'm talking about this phase. Basically these guys here, cesium, octahedral cesium. Yeah, it's definitely possible, but I just like to see what evidence they have for it. Okay, they talk a little bit about the XPS, maybe we'll come on to that later. The structural change during the transformation reaction can also be reflected by the Raman spectral evolution 2D. The Raman peak at 259 wave numbers corresponds to the symmetric structural mode of the bismuth chloride octahedra. After introducing the silver component, a shoulder-like Raman feature emerged on the high binding energy side. I think they mean high frequency side. I think they got a little bit too obsessed with I'm trying to turn this phone off. This phone won't turn off. So they got a little bit obsessed with XPS. I think they mean high wave number or high frequency, because that's all about Raman, which is due to the bismuth chloride bond length shortening of the bismuth chloride octahedra upon lattice contraction. With increasing silver concentration, the intensity of the newly emerged peak became more pronounced, along with a gradual intensity decrease of the initial Raman peak. In addition, the new Raman peak continuously shifted to a larger wave number from 274 to 281 wave number, suggesting a bismuth chloride shortening process. Such results agreed. I should zoom out a little bit, makes it a little bit easier to scroll around. With the XRD measurements showing continuous shrinkage of the bismuth chloride octahedra upon increasing the silver concentration. Moreover, the peak of bismuth chloride octahedral scissoring mode became more defined, further supporting the increased crystallographic symmetry with simplified neighbouring cesium environments. Okay, so the Raman is telling you about the vibrational properties of this material. So they're saying that again we get a nice change, I think, between the starting and end points. I think it's maybe less. They make some conclusions there. I think it's maybe less obvious compared to the XRD what's happening. To be honest, the starting Raman pattern and the ending Raman pattern look pretty similar, and the intermediate ones just kind of look like a mixture between the two. So I don't know how far that gets us, to be honest. I don't at the moment see any kind of strong evidence for cesium on the silver side. Cesium on the octahedral side. I think there's good reason to believe it could happen, but you know, maybe there's some ways to probe that. They don't seem to. Okay, no, here we go. They do mention it. Increasing silver concentration. Here we go. Sorry, we just haven't read far enough. Increasing silver concentration leads to the partial phase transition from 0D to the alloyed DP phase, where both AgCl6 and cesium-Cl6 octahedral units are formed by sharing the corner Cl ions with bismuth chloride octahedra inside each nanocrystal. In this process, the double perovskite crystal motif emerges and coexists with the pristine 0D perovskite structure. With further increasing the silver concentration, the intermediate alloyed crystal motif progressively dominates the crystal phase of the nanocrystals, where the silver concentration reaches a sufficient level to fully occupy the M1+ sites of the double perovskite structure. The pure material is obtained. Okay, so again, they don't. So they're kind of describing it, and we described it before. I don't see. This is all super plausible. I can really believe all of this. I'm just interested by the cesium on an octahedral site. To me, it's just a little unusual in these structures. Maybe it's not. Maybe there's loads of examples that can be given out. But definitely a really nice series of experiments, taking the XRD at each stage, taking the Raman at each stage, taking the TEM at each stage, taking the XPS at each stage, taking the EDX. I think they did energy dispersive X-ray analysis, and I think down here they even do taking the evolution of the absorption spectra. So immediately they start to see, it looks like immediately they start to see photoluminescence, the absorption and photoluminescence. Immediately they start to see photoluminescence, and you can see the kind of evolution. Let's zoom in on this a little bit because it's pretty interesting. The evolution of the absorption spectrum as they go through that reaction. So I think I'm going to have to bring it all together reasonably soon, so we won't have time to go through the whole paper, unfortunately. But I think a really key idea here is that they are able, with all of these different techniques, with the XRD, with the TEM, with the XPS, with the photoluminescence, with lots of different things, to monitor the reaction as it's going on. Yeah, so how is this reaction actually occurring as the silver is inserted in there? And they come up with, bringing all these things together, they come up with a pretty plausible kind of mechanism for this to happen. So this is going back to their original point. This is one of the, I think, the advantages of being able to do this reaction in kind of super slow motion. By doing this super slow motion reaction, you can actually get an idea of what's happening, and they build, you know, a pretty convincing case for understanding the mechanism here. Right guys, I'm going to have to bring the stream to an end. We've got there's a little bit more on the optical properties which would have been nice to explore, but I think hopefully you know, I think we've got a good flavour of what this paper is about. A lot of the kind of themes of the synthesis, of this indirect synthesis, some of the challenges of making these nanocrystals, some of the maybe kind of interesting methodology there. Really nice paper. I'd advise you, you know, if you're interested in this area, definitely go have a read of this paper. Really good work here, very nicely explained as well, I think. So thanks very much for joining me on this stream, guys. It's been really good to have you here. This is going to go, if you missed anything, this is going to go on YouTube in reasonably short order, so you'll be able to watch about there. And yeah, feel free to follow, feel free to watch on YouTube and like on YouTube, or you can always follow on Twitch, and you will be notified whenever we go live with a stream, so you will not miss anything. Thanks very much for joining us, guys. Great to have you as part of the stream. I will see you hopefully on a future stream in not too long. See you later.